Welcome everyone. So now that we have discussed analysis of variance in the previous video, now I'll show you two examples taken from your textbook, which is Statistical Methods for the Social Sciences by Agresti and Finlay, 4th edition of the textbook. So in this episode I'll give you two examples, one of a single factor ANOVA, which is also known as one-way ANOVA, and the second one with two-factor ANOVA, that is, there will be two sources of variation, and we call it two-way ANOVA. So the first example is given on page 370 of the textbook, and there you'll find in table 12.1 you find some summary observations on political ideology for three groups based on political party affiliation. So in this problem, the outcome or the response variable is political ideology, and that was measured on a 7-point Likert scale. And the explanatory variable or the regressor variable is party affiliation. So party affiliation is a categorical variable, and the response or the outcome variable is quantitative, measured on a 7-point Likert scale. Okay, so here's the summarized data. If you look into the column, in the first column it shows the group or the party ID, three categories, and the political ideology on a 7-point Likert scale, and these are the number of Democrats who have scored a 1 on the political ideology question. So in total there are 91 Democrats and 111 independent, and then 74 individuals who identified themselves as Republican. Okay, so this is summarized data, and we actually have 276 observations in the original data, but we do not have the original data. So I've created the original data based on the information that we have in this table. So here's the data look like, and I have created a data set, and I call it political_1.csv. This is a comma separated value data set that you can open in Excel, and you can also import into SAS. So now let's import the data into SAS using the following SAS statement. So for your case, you have to change the path information appropriately. Okay, and this import data will be saved in a SAS data set called political. Okay, so now after we import the data, so we run some frequency analysis, frequency distribution. If you look here, this table exactly looks like the same that is given in the textbook. Okay, now we'll do some descriptive statistics again, just to confirm that the descriptive statistics matches with the values that we have in the textbook example. So here we have calculated means and standard deviations of these scores on political ideology by their party identification. We will run a one-way ANOVA analysis of variance using PROC-GLM. So here party identification is a categorical variable, so we have to declare it as a class variable, and then the model statement we write this way: the score is the outcome variable, and then the party is the predictor variable. So the outcome variable, the response variable, and the predictor variable is the party. Now why it's called a one-way ANOVA? This is because we have only one source of variation in the scores, in the data, and the source is party affiliation. And also notice that in the model statement we have only one predictor variable that is being used to predict the scores. So that's why it's a one-way ANOVA. Now we want to compare the mean political ideology scores and by party identification. So we're testing the null hypothesis because we have three parties that the respondents can identify themselves with. So our null hypothesis is essentially whether whether the means of the political ideology scores are the same across party identification. And the alternative hypothesis is that at least one of the means is different, or at least one pair is different. So that's our null hypothesis. And SAS will give us the ANOVA test result, and this is the ANOVA table. And again, the model statement it captures or represents the between sum of squares, and the error represents the within group sum of squares. And we have discussed this in details in the previous video, and here we find that the F statistic value, which is obtained by dividing the mean square for the model by the mean square for the error. So we got a very large F value, large compared to 1. So and the p-value is really small. Okay, so how do you make a decision based out of this ANOVA table? So we see that F test statistic value is quite large and the p-value is quite small. So the p-value, again, it represents, or it gives you the likelihood of observing this value of the test statistic, or more extreme than the one that we have observed, if the null hypothesis was true. So the likelihood of observing this value if the null hypothesis were true is really small. So that indicates that our null hypothesis might not be true. Okay, so there is strong evidence that the null hypothesis may not be true. So therefore we conclude that there is statistically significant difference between the mean values, between at least one of the pairs of the means. So when we reject the null hypothesis and conclude that there is significant difference, what does it mean? It means that the population mean scores on political ideology across the three groups political party affiliation are different. So the mean scores in the population are different across political party affiliation. So in other words, the average political ideology scores differ among those who identify themselves as Democrats, Independent, and Republicans. So that's all we can get out of an analysis of variance. Now, what we can't get from the ANOVA test results. So this test result do not tell us whether the differences are due to the difference between Democrats and Republicans, or between Independent and Republicans, or between a particular pair. All we can say is that there is a difference between these three political parties. So in order to identify why there is a significant difference and which particular pair is significantly different, we have to carry out some post hoc tests, which I will discuss in some other videos. So now let's take an example of two-way ANOVA. So two-way ANOVA means there will be two sources of variation, or two regressors. So we can build a model without interaction, without interacting the two regressors, or with interacting the two regressors. So we can build models that involves only the main effects, that is the regressors will not interact. And also we can build a model where the regressors will interact, as well as the main effects. So we'll use the same example, but here we'll use a slightly different data set, and the data summary is given here. So now look at that. Here we have the same variables, the party identification, the party ID, the political ideology scores, but this time we have added another variable, gender. So these scores are distributed by male and female, by the gender. Okay, so again, this is the summary data only. We have to create the data set, and I have already created it for you. You can just import that data into SAS and carry out the analysis. Our research question is if there is any difference in the mean scores on political ideology. so whether there is any difference. But this time we have two sources of variation. One is the party identification and other is the gender. So we would like to know if party identification has significant effect on the differences on the average scores on political ideology, and also we'd like to know if gender has any significant impact, and also we would test if party identification and gender interact. Okay, first of all, let's ask why it is an ANOVA. So it's ANOVA because we're trying to answer if the population mean scores on political ideology are different across party affiliation and gender. And why two-way ANOVA? Because there are two sources of variation, or two regressor variables for the political ideology scores. So one is the party identification and other is the gender. So the hypotheses that we are testing here are listed here. So we have two sets of hypotheses, one for party identification and the other for the gender. For the party ID, we have three levels, meaning three types: Democrat, Independent, and Republican. So the null hypothesis would be whether the average scores are different. So this mu1 equal to mu2 equal to mu3. So that's the null hypothesis, and the alternative hypothesis is that at least one of them are different. Similarly, for gender, we have two levels. So we are testing if the average scores on political ideology is the same, or if they are different across the gender. So the null hypothesis is mu1 equal to mu2 against the alternative is that they are different. So we have to prepare the data for analysis, and I have created the data set and saved it in a CSV format, and we'll import that data into SAS, and that's the same SAS code. Here we have the second data set, which is political_2, and then we are creating a SAS data set, and we are naming the data set as political2. Okay, so now let's do some descriptive summary statistics, the mean, standard deviation by party identification and by gender, and again which exactly matches with the numbers that are given in your textbook. Now we use procglm to run the analysis, a two-way ANOVA without interaction between the regressors. So this time we are not considering interaction between the regressors. So this is how we write the model statement: score is your outcome variable equal to party and then gender. So these are the main effects. These are the two sources of variation. The ANOVA table is given here, and the individual significance, the test for individual significance of each of these regressors is given in this table. Here we get tests for main effects, and this one is the overall ANOVA table. And we're going to interpret these two tables in the next few slides. This is a two-way ANOVA without interaction. From the ANOVA table, we find that taking the two predictors together, that is the party ID and the gender together, there is significant difference between the mean scores on political ideology. Okay, so this large test statistic value and a very small p-value suggests that we have reason to believe that the null hypothesis were not true. Okay, so that's this ANOVA table tells us. So which is good. So we can go ahead with this analysis and test for the individual significance, individual importance of each of the regressors, and that we get from this table. This is a type 3 sum of squares table. If you run this analysis in SAS, you will find that there is another table that's called type 1 sum of squares. Again, for the most part we will use only type 3 sum of squares, and the details are not within the scope of this course to discuss, so we'll just use the type 3 sum of squares values. Okay, so here we test whether the party variable is significant on the scores, and whether gender has any significant impact on the scores. Okay, we'll look at the p-value, p-values for each of these regressors, and by looking at the p-values we see that party identification is significantly impacting the scores, the difference in the scores. So in other words, party variable is significant while the gender variable is not, because the p-value is very large, right? In this model we haven't considered the interaction, the joint effect of party and gender on the scores. Okay, we will now consider a model where we will include the joint effect, the interaction between party and gender. So two-way ANOVA with interaction. It is important to study the interaction between the regressor variables before concluding the results of a model which includes main effects only, the model that we have just considered. Okay, so we have to before we use our results of the previous analysis, we have to consider interaction in the model, and the reason is, if there is a significant interaction, then the main effects do not have straightforward interpretation, because the predictors are interacting with each other, so it will mask the individual contribution of each of the predictors on the scores, on the outcome variable. Okay, so we need to take the interaction into consideration. All you need is to rewrite your model statement. You keep the party gender and you add this interaction effect by multiplying party and gender. Okay, so that's how you do it, and this gives you again the overall ANOVA table and the individual tests for each of these predictors. Now we have three predictors, right? We have party, gender, and the interaction between party and gender. Okay, so here the p-value is really small. This suggests that we can reject the null hypothesis that the population means are all equal across party and party identification and gender. So overall there is significance, so which is good for us to go ahead with further analysis. Now we want to test for the interaction, right? Our null hypothesis is that there is no interaction. In other words, the coefficient for the interaction variable is 0. Okay, in other words, we are testing if the interaction is significant. So we'll look at the p-value again, and looking at the p-value we see that interaction is not significant because it has a large p-value. So in other words, there is no significant interaction between the party and the gender. Here is the interaction plot for scores. Here, look at that. We have scores. Okay, so these are the average scores on the y-axis, and in the x-axis we have party ID. And in this plot, in this overall graph, we have actually plotted three variables. These two indicators, a /0/0 with different colors of course, but this /0 represents the gender. Okay, now the blue one represents the female, and the red one represent the male. Okay, and these are the average scores. And if you look at that, if there is interaction between the party identification and gender, then these lines will cross. So what it means is that if you are a male, then the average score on political ideology will increase if you are Republican as opposed to Democrat. You see that there is an upward going straight line, okay, which is not the case if you are a female. You see that the female Democrats have a higher score than the male Democrats, right? Look at that. And then somewhere in between it changes, and that indicates an interaction. If there were no interaction, these lines will be parallel. Okay, there will be no crossing, there will be no interaction. However, the interaction that we have here is really small, and that is why the statistical test could not find a significant interaction. If there were a significant interaction, then the line would cross at a much steeper angle. Alright, so to summarize, since the interaction is not significant, we should normally be considering a simpler model without the interaction term. That is, we would consider a model with only the main effects, party ID and the gender. Even when the interaction was not considered in the model that we have previously considered, only the main effect of party ID was significant and the effect of gender was not significant. So this means party affiliation has statistically significant effect on the scores on political ideology. And that concludes this episode. Thanks for watching.